In this video, we're going to talk about randomness, probability, and simulation. When you think of probability, you might think of flipping a coin, or rolling a die, or picking a name out of a hat, something that would include chance. So chance behavior is unpredictable in the short term, but has a regular and predictable pattern in the long run. We call that probability. So the probability of an outcome of a chance process is a number between 0 and 1, or 0 and 100% if you like percentages. And that describes the proportion of times the outcome, so however many dice rolls you had, or the number of times you flipped a coin, those are all outcomes. So the proportion of times the outcome would occur in a very long series of repetitions. So probability holds when you do things a lot of times. So that is due to the law of large numbers. That says that if we observe more and more repetitions of any chance process, like flipping a coin or pulling a card out of a deck, the proportion of times that a specific outcome occurs approaches its probability. Just a little baby note here that some people use the phrase law of averages to refer to the misguided belief that the results of a chance process have to even out in the short run. So that's when you flip a coin and you think, oh my God, I've gotten tails 7 times in a row. The next one has to be heads. Wrong. That's not how probability works. Coins and dice and cards, they don't have a memory. So they don't really care if it evens out or not. So in order to model chance behavior and estimate probabilities, we do that with something called a simulation. And that is the imitation of chance behavior based on a model that accurately reflects the situation. So what is the process to a simulation? Well, let me tell you. So you describe how to use a chance device to imitate a real one, so that's repetition, of the simulation. And then you tell what you will record at the end of each trial. So are you going to be flipping a coin, pulling cards, whatever it is? That is going to be the trial. What are you doing? And then you perform many trials. In fact, you could have technology perform those trials if they can be programmed to do such. And then you use the results of your simulation to answer the question that you posed at the beginning. Now let's look at an example of performing a simulation. So this one has to do with NASCAR cards and cereal boxes. Now remember, NASCAR is the thing where you get in a car and you drive around a loop over and over and over again. Sometimes you hit things, sometimes you flip over. Woo! What a ride. So the problem says, in an attempt to increase sales, a breakfast cereal company decides to offer a NASCAR promotion. So each box of cereal will contain a collectible card featuring one of the following drivers. So we've got a Joey, a Kevin, a Chase, a Danica, or a Jimmy. So the company claims that each of the 5 cards is equally likely to appear in any box of cereal. So they must have produced the same number of cards. A NASCAR fan decides to keep buying boxes of the cereal until she has all 5 drivers' cards. God, she must love that cereal. She's surprised when it takes her 23 boxes to get the full set of cards. Does this outcome provide convincing evidence that the 5 cards are not equally likely? To help answer this question, we want to perform a simulation to estimate the probability that it will take 23 or more boxes to get a full set of those 5 NASCAR collectible cards. So first up, let's describe how to use a random number generator to perform one trial of the simulation. And the dot plot here shows the number of cereal boxes it took to get all 5 drivers' cards in 50 trials. So let us take the 5 NASCAR drivers and label them 1 through 5. So Joey's 1, Kevin's 2, Chase is 3, Danica's 4, and Jimmy is 5. And we'll generate a random integer from 1 to 5 using technology to simulate buying 1 box of cereal and looking at the card that's inside. So that generation is going to be with replacement. So I'm sure you've done this before in your life. I certainly have. You buy something, you look inside, whether it's a card or not, whatever it is, and if you can collect them all, right? Sometimes you get multiples. That's how they get us, us consumers. So you keep generating random integers until all 5 labels from 1 to 5 appear, and then you record the number of trials or simulations that it takes to get all 5. All right, now that we have an understanding of how all these dots have been produced, or the number of boxes required in each of those simulations that were performed, let's now explain what the dot at 20 represents. So if you look at simulated number of boxes required, that would mean that there would be 20 number of boxes required. So you had to pick 20 random numbers in order to get all 1 through 5 or all 5 cards. Last but not least, let's use the result of the simulation to estimate the probability that we'll take 23 or more boxes to get a full set of cards. Does this outcome provide convincing evidence that the 5 cards are not equally likely? First thing I did is I found where 23 would be on our dot plot, and I noticed there's no dots at 23 or to the right of 23. So that tells me that the probability is roughly 0 out of 50, because there were 50 trials. And that would mean that there's a 0% chance it would take 23 or more boxes to collect a full set of cards. So because that is so unlikely that it would take 23 or more boxes to get a full set, this result provides convincing evidence that the 5 NASCAR drivers' cards are not equally likely to appear in each box of cereal. All right, now I'm hungry. I'm going to go search for some cereal. That's going to do it for this video. Thanks for watching.